Okay, welcome everybody. This is Tech Tuesday, brought to you by CamLogic. My name is Josh Kolcan, and today's topic we'll be talking about strong functional parts from 3D printing. As many of you know, 3D printing is used widely throughout the world now for rapid prototyping, some manufacturing, a lot of cool stuff going on with this right now. So we're going to jump right into this. Just a quick overview of who CamLogic is and where we're heading. They were founded in 1995 in Oxford, Michigan, covering Michigan, Ohio, Indiana, and Pennsylvania. Got a great proven track record. Industry expertise, cutting edge product and services. We have highly trained staff, dedicated customer service. Everybody here at CamLogic is excited to be in this industry and would love to see everything moving forward. So real quick, we're just going to touch base on what kind of 3D printing technologies are out there now. They're not all on here, but these are some of the heavy hitters that are in the industry. So first we have multi-jet printing. Multi-jet printing basically means that we have one big print head with a multiple array of jets jetting out different types of material, one usually for the support material and one for the build material, whether that is an acrylic or something else. We're not going to be talking a whole bunch about these other printers. I just want to touch base and let you know what they were. FDM, most people have heard of, fused deposition modeling. This would be your Stratasys type machines, MakerBots and stuff like that. Good units. Another one is SLA, stereolithography. Now this is very, very old technology, very good technology, very good surface finish, very high accuracy. Strength is mediocre with this type of technology. Color jet printing is used as a gypsum powder based printing that is essentially glued together layer by layer. This is an awesome show and tell printer, but as far as a functional usable part, it's not really meant for that. What we will be talking about mostly today is FFF, fused filament fabrication. Markforged has come up with this, and this is solely for Markforged as far as this type of technology is named. Some of the topics that we will be covering today, we're going to touch base on file preparation, splitting parts into multiple pieces. So if you have a part that's too big to fit into your print build chamber, we can cut those parts and get those to fit in. Part placement and orientation, what types of fiber, adding fiber reinforcement, layer height and resolution, internal fill patterns and densities. So these are all the topics that we will be digging into today. First is file preparation. And here you can see, like with most 3D printers, we need to start with a good watertight STL. Now, I'm not going to dig a whole bunch into this, but we will just touch base with this. So what is watertight? Watertight means that we have no holes in this model. Essentially, if we were to fill this model with water, would it leak out anywhere? And here on the right, you can see in the red that this is a watertight model. There is no holes in this model whatsoever. It's a nice clean STL. Shouldn't have any problem printing this. The one on the left in the yellow, this is actually scan data and a little bit of missing data which created holes in these STLs. Now, this is obviously not a very good STL. You can see all these marks and everything in it from the actual scan data, but this was more just to show you what a hole in an STL would look like. In these blue areas down here, these are actually holes in the STL. So if we were to fill this full of water, water would essentially leak out of these holes. And you want a nice high resolution STL file, so you don't want to see any blockiness to this file. You want to see nice smooth curved surfaces where you have nice round features. And the other thing is that we need to make sure is we don't have really super thin features in any of these models. For the FF style printers, they are an extruded type printer, so they need to be so thick in order to essentially build correctly. And if we get below that minimum thickness, then we're going to start running into some issues. Now, this is about all we're going to dig into here. Chris Himberg has actually done a really good Tech Tuesday that is on YouTube about files and STLs and everything. I encourage you to take a look at that link and watch that video. It's very helpful, very knowledgeable guy. He did a really good job. Splitting parts in post-processing. So the best way to, if you have a part that won't fit into your build envelope in your printer, the best thing we can do for that is to, one, either scale the part, or if that doesn't work, then we need to actually cut the part. There's many softwares that can cut the parts, and there's many ways of cutting the part. One thing that you really want to keep in mind is where you're cutting this part at. We have a tendency to want to cut parts right in the middle, which is not necessarily always the right thing to do. This particular part here, if we were to cut it in the middle, it would be one of the thinner areas of the part, and it would actually create, you know, another weak point right here because it's so thin. So what we'd essentially want to do is, this is a little drastic, and I just did this for demonstration purposes, but we would want to cut this back here in the model where it's nice and thick, where we've got a lot of meat to glue these two halves back together. So what you would do is you would go into whatever software that you're going to cut it. This one I'm using Magix, but you can use whatever you have available. And you can cut this part in half or in thirds or whatever you needed to do, get inside the printer. Well, we can go over here and we can hide the unselected. And if you look down, it automatically creates another watertight STL when we do that. So after we cut this, we just save these two out as separate STLs, and once we get them into the printer, they will print as two separate STLs. That's easy enough said and done. So how to glue these parts back together. Now this, again, is pretty much solely for the Markforged and their materials. So what they recommend is actually Loctite 410 is one of the better glues that they have come to find works very well for their materials. Now since their materials are nylon based as far as the two base materials go, this glue works very well and actually can be sanded and smoothed out. Best sanding methods include 220 grit sandpaper usually and wet sand to create the best finish. You can use higher grit sandpapers, but you will find that it leaves kind of a grainy surface on the part. So what I recommend is 220 grit sandpaper, wet sandpaper, and just sand the parts like you would any kind of you know, piece of furniture or wood until you get the desired smoothness. Part placement is one of the most important things to understand. So I'm going to jump into the software over here, and so this is the actual Eiger software for the Markforged printer. And as you can see, I have the same part in here that we've been working with. These were actually vice jaws that we needed. We do also a lot of in-house scanning, and we needed soft jaws for our vice to clamp you know, nice machine parts that we didn't want to put little dents or divots in, so we can scan them. So we actually had printed these out of our Markforged and put them onto the vise so we could clamp parts without hurting them. So part placement and orientation. First thing you've got to think about is how this printer works. So this printer is going to lay down layer by layer of material and essentially keep gluing these layers together and together. Now, if we think about this part and how the force is actually going to be applied to this part is going to tell us a lot on how we want this printed. So these are vice jaws. Most of the force that is going to be applied to these jaws is going to be on this surface right here. On all these surfaces right here is going to be where all the force is applied as these two jaws come together to clamp the part. So ideally, this would be the way that we would want to print this. Why we wouldn't want to print it any other way, so let's just say that we wanted to print it like this. Which, yes, this would print just fine. One thing we would have to understand is when we print this now, we're going to have some support structures in here, which is not a big deal and not a major concern. My major concern with printing it like this is if we clamp something over here onto this end of the jaws over here, this part tends to kind of want to warp and bend because we're only putting pressure on one side of it. So if we have layers going this way, we're putting stress on each one of these layers that essentially it's going to fight us on trying to rip these layers apart if they're layered like this. So we have the stress going this way on the part. So that obviously is not ideally way to print it, and plus it's going to increase your print time. And we also want to add some fiber to this, which we'll get to in a minute. So we can come back over, go manual registration, and flop this back down. Maybe. There we go. Okay, so this is how I would print this. Again, there's not really a right and wrong way to print this. Because the materials are so strong with the Markforged, we really wouldn't have too many issues as far as that, but for best practices we would want to lay this flat. For one, we can get a lot more fiber in this part, and we don't have support structures, and all our layers are going to be going this way instead of this way, which is going to give us more strength for actually compacting this part. Okay. So to limit part warping, we can do one of two things. Part warping usually is associated with heat. So what happens is you have a really thick part, and as you laying down this hot extruded material, the part tends to heat or tends to cool at different rates, and anytime anything cools at different rates, molecules and everything do all kinds of funky stuff inside, and they start, trying to pull away from each other and push together, and that's when you actually get your warping. So in order to limit warping, we can do a couple things. One, we can run fiber in the part that will limit warping. Another thing we can do is use a brim. So what a brim is going to do is the brim is actually going to essentially put a border around this part to help hold it onto the build plate to keep it from warping. Other things we can do is to position and build in different ways so that we are deflecting heat better. So essentially the part is not as thick as it has to be. We can also expand thin features if we had some thin features on there that could reduce warping, but not necessarily going to fix all our problems. Usually the brim is going to be one of your best bets, and also when you add your fiber reinforcement into the part is also going to help tremendously on that part warping issues. Okay, so what types of fiber do we have? We have carbon fiber. As many people know, carbon fiber is used very, very much throughout the world, from anything from drone propellers to carbon fiber spoilers on race cars. The uses are pretty much limitless for carbon fiber. It's replacing a lot of steel components. The strength to weight ratio is, extremely high, and we're, finding all kinds of ways to use this carbon fiber. Kevlar. I'm sure many people have heard of Kevlar as in bulletproof vests and stuff like that for the military. Well, a lot of people don't notice that Kevlar is also used for abrasion resistance too. As you can see up here in the right hand corner, these are actually Kevlar gloves for an assembly line or something like that they have incorporated Kevlar into the actual material so that they can pick up sharp objects without worrying about getting cut. Fiberglass. Fiberglass has been around for a long time. It's very cheap reinforcement to run. Many boat hulls and race cars, Corvettes, and everything like that, a lot of those are made out of fiberglass parts. They also offer a high strength, high temperature fiberglass. This application, this would be used if you needed a model that had to withstand some serious heat. So in order to jump into these fibers, we're going to show you how these actually are into the software of the Eiger software. So what we have real quick is we just have one of two base materials. We have a nylon and an onyx. In this particular case, we're going to pick onyx. So what we need to do next is figure out what kind of fiber that we want to use for this part. Now, one thing to consider is how is this part going to be used? Obviously, these are vice jaws like I explained earlier, and the compression force on these is going to be pushed in this direction into the Z direction. There's a couple different, we could do carbon fiber in here, and it would be just fine, but realistically for this particular application, we would want to run Kevlar. Now there's two reasons that we want to run Kevlar. One, Kevlar is abrasion resistant, so that's going to make these jaws last a lot longer. If we're sliding parts in and out of here, all day long, these are going to wear out eventually. So the Kevlar is going to give us that wear that we need. It's going to withstand quite a bit of wear and tear on these parts. Also, Kevlar is very good at resisting compression. So when we're clamping parts in here and we're squeezing these and we're trying to essentially push these together, this Kevlar is going to kind of give it a lot more reinforcement so we don't have that compression as bad as to worry about. Carbon fiber is very, very strong, very, very good, but carbon fiber can also be brittle too. So we have to keep that in mind. Again, what kind of parts are we making is what this is boiling down to. We could do fiberglass. Fiberglass is a very good reinforcer. It's very cheap to run. But for this particular case, like I said, we are going to go with the Kevlar. And the Kevlar, the Kevlar is yellow. Each one of these materials has a little bit different tinge of color to it. When we're running the onyx material, this doesn't really matter because you're not going to see it, but when we are running the nylon material, then you will actually see this fiber fill pattern inside the part. And we will jump into what this actually looks like inside in just one moment. All right, so adding fiber reinforcement. How does fiber work? All right, so how does the fiber work? So essentially we will show you that right now as we jump into the internal view of this part. Now I'm not jumping into every nooks and cranny of the software. This tutorial or this YouTube video is not really for the Eiger software. This is more about the strong functional parts that the Markforged printer can make. So what we're going to do is we're going to jump into here, and we're actually going to see our part now right now in 3D, but we can also switch to 2D. So this is that brim that I was talking about. This is that border that's going to keep this part from warping, or at least help this part from warping. Anytime that we have a 3D printer that's using heat, warping can be an issue. So we want to eliminate that as much as possible. So that's what you see here. So I'm just going to go ahead and click the visibility off of this brim just to make this a little bit cleaner, just so we can see the part a little bit better. So we have the Kevlar, and if you look down here on our bar here, all the white here is what the onyx material is, and the yellow is the Kevlar. So how this works is there's two ways to lay in fiber. One way is to have a concentric rings around the part like this, or the other thing we can do is do isotopic. So isotopic basically means that it's going to do a zigzag crisscross pattern inside the part. Now, what are the differences and why would you want to use one versus the other? That's a very good question, and this again all goes down on how the load on the part is going to be. So for these particular vice jaws, most of the load is going to be in this Z direction. So if we see the rest of our part, most of our load is going to be in this Z direction, right? We're going to be clamping stuff in here, so these are going to be compressing down this way. Particularly on this one, it really doesn't matter. I mean, you could kind of use either or, but I typically like the concentric better, just strictly because, like I said, if we do clamp something on this side of the part, I don't really want these jaws over here to start warping and trying to pull themselves apart. So I want, you know, this really strong, rigid outer box of this thing. So like I said, this yellow is the Kevlar, and we can change all this. So one thing to keep in mind here is there's a start and a stop to all of these fiber layers. And if you can see right here, this actually starts right here and comes all the way around as one continuous strand until it gets over back to here, and then it stops. Now this looks good and everything, but one thing we don't want to do is have the fiber start and stop on a weak point in this part. So what we can do is we can actually change where these fiber layers are starting and stopping. So if you just saw that, this moved right here. If you didn't, I'll do it one more time so we can see. We'll do something really drastic, like 35. Okay, now you can see these fiber layers had started and stopped way over here. We don't really want these in the middle. If you can come back to here and, you know, imagine this is it's going to be our weak point right here, right? We got the least amount of material. It's in the very middle of the part, far away from the bolt holes. So we really don't want to start and stop our fiber fill right in the middle of the part. So that's why if you come back over and you see where I did that, oh, I guess it changed over. So see, it was starting and stopping over here. We did over here. You really wouldn't want this fiber to stop and start in the middle. Again, this is creating, you know, a weak point in this part. Not necessarily a weak point is the wrong way to say, but not as strong as it could be. So just want to keep that in mind. Also, one thing to understand is how much fiber do we want to put in this. Now, this is a cost benefit for you to limit the amount of fiber that you are adding to your parts. The more fiber that you put in your parts, obviously the more expensive it's going to be, and it is also going to increase your print times too. So just keep that in mind. We don't necessarily, I mean, we could fill this whole thing up with fiber if we wanted to, and it would be, you know, really strong part, but completely unnecessary for what this application is. I really haven't had too many applications where you're going to need to fill a part 100% up with fiber. A lot of times you can limit areas that you want the fiber to actually give a part a little bit of flexibility to, and not have such a rigid part in all areas. You cannot just use fiber alone to print. How these printers work is they have to lay down a base material. Like I was saying, that onyx or the nylon would be your base materials. Now to each one of these base materials, then you can add your fiber. Again, adding fiber to your parts is for strength and abrasion resistance. If you look down here, it's a little bit hard to see, that's why I did this yellow one, but on these is actually a set of channel locks that we printed over here. And as it was printing, I just snapped a picture just to show the internal fill pattern and the actual carbon fiber that is being laid down into this part. Now you can kind of see in a little bit here on this one too, this one's actually Kevlar and onyx, and it's a lot easier to see. But there's the internal fill pattern, and how this works is it actually smushes this Kevlar down. So all these fiber materials actually come with a little coating of nylon on the outside of them, and as it goes through the extruder, the nylon is heated up, and essentially the print head smushes this Kevlar layer down into the previous layer of the part. So it creates a nice flat surface of this fiber fill. Layer thicknesses. These can be very crucial to part strength. Now if you look over here, these are pretty drastic changes, but just so we can see. So over here we have 50 microns, 100 microns, and 200 microns. Now, not only is obviously the 50 microns versus the 200 microns a lot more aesthetically pleasing, but it is also going to be a stronger part. So these are the 200 micron layer thicknesses are obviously going to print much faster. You're still going to use the same amount of material, but you're going to have a lot faster print times. Saying that, you're also going to have a weaker part. So picking a layer height that is best for your part and best for your time is going to be something that you need to understand. One thing is how aesthetically pleasing do we need this part? Is this just a big robust part that we need very fast, and we don't really care exactly what it looks like? Then you might want to go with a higher layer height. Now keep in mind also with the higher layer height, you're going to lose a little bit of accuracy and strength. So again, this is a lot of understanding your parts and knowing what to do with them. Internal fill patterns and densities. So there's a couple different ways that we can do fill patterns inside these parts. So down here, if you look, there is a cutaway of a race car wing support, and this is just showing carbon fiber and nylon in here. Again, these are just the pictures that I took while this was printing, and you can see our internal fill patterns. I'm going to jump into the software real quick, and we'll run over just a real quick brief what these internal fill patterns can look like. Okay. So these are the different types of fill patterns. So there's a rectangular fill, a triangular fill, and a hexagonal fill. Generally speaking, depending again on your part's geometry and how it's being used, this is going to matter on which type of fill pattern you pick. Usually I run with the triangle fill pattern just because triangles are very strong shapes in pretty much any direction that you apply on them. So that's what I normally use, but depending on what type of part it is and where the loads are being put on this part could also make you change into a different type of fill pattern. As you can see, these well, here we'll change this to hexagonal, and we can actually go inside and see the internal fill patterns of this in a 2D mode. It'll be a lot easier to see. Just give it 1 second. So we're going to come over here to internal view, and we're going to go into 2D. Now, oops. Now these are the actual internal fill patterns of this part. So we're going to take a couple of these off just so we can see this a little bit better. Okay. So these are the fill patterns, and as we come through the part, we can see how they change from back and forth and back and forth and back and forth, right? So we don't want all our fill patterns going in the exact same direction. We want this kind of X pattern or crisscross going on throughout the part to give it the most strength. So this will be very strong and very useful, and as you come through here, you can actually change the different types of fill patterns inside the part too. As you can see now, we have this honeycomb, and these are actually just the cutouts of those jaws themselves is what we're looking at. And as you can see, as we get back to the top, we come back to this other type of fill pattern. Now you can play around with this and, you know, figure out again what types of loads are being put on your part, and how these parts are going to be used is going to be a very good determination of which types we need to use. Now all parts are different, so there's no real silver bullet on this one. Excuse me. Walls, fill density. I'm sorry, almost skipped that one. So if we go back to the part view, fill density is pretty easy to sum up. Fill density essentially is that internal fill pattern that we just discussed, those triangles, that honeycomb, all this stuff is how, think of it as all these triangles. How many triangles do we want inside this part? Minimum fill density, you know, you're going to have very big triangles, very spaced far apart. Your minimum, they're going to, you know, have a ton of triangles in here spaced very, very close together to give this part the most strength that we can. Our walls and our wall layers and our roof and floor layers. So basically what this means is how many layers do we want of solid material on the tops and bottoms of this part. Now in this particular software, they've got this set for roof and floor layers to 4 and wall layers to 2. So what that means essentially is on this side wall right here, whoops, I really didn't mean to flip that part. On this side right here, we're going to have 2 complete solid layers going up this vertical wall right here. And on the roof and floors, which would be on this and actually underneath the part here, we're going to have 4 layers. Now these are factory set and they seem to work pretty good. If you did need a part that maybe, you know, you were going to have something that was sharp or really hard pushed against one of these surfaces, you might want to up this just to give yourself a little bit thicker of that solid, that complete solid surface on here, just so we don't, you know, aren't punching through and getting into that fill pattern. So we could, you know, jump this up and, you know, go all the way to 10 if we want. Again, you're going to use more material and you're going to increase your print time a little bit, but it really depends on the application of your part. And that about sums it up for today. I hope to see everybody again, and we will have more videos to come. Hope everybody has a great day, and thank you for joining.